Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 12, Modeling Using Similarity. So there's nothing new in this chapter section except application in real-world situations. So we're going to use the angle-angle theorem. We're going to use the proportional sides method and probably triangle sum theorem. Everything that we've already done is all going to come together in this video. So the first example says, not all flagpoles are perfectly upright, meaning perpendicular to the ground. So in other words, this is not a 90-degree angle. Some are oblique, which is what we call two lines that are neither parallel nor perpendicular, or right angles. Imagine an oblique flagpole in front of an abandoned building. So here's a portion of the ground they're showing, and here's the flagpole in the ground, and it's not perpendicular with the ground. The question is, can we use sunlight and shadows to determine the length of the flagpole? So what they're saying here is, if we have a sun and it's shining bright today, okay, then it's going to shine a ray down like this, okay? Or actually, I think I'll move it because I've done this in class and I know what the outcome is. So I'm going to be a little steeper here. So here's the sun, and it's shining down. So the shadow would be right here. So here's our sun shining. Here's the top of the flagpole. So it says, assume that we know the following information. The length of the shadow of the flagpole is 15 feet. Okay, so that means this whole distance here is 15 feet. There is a mark on the flagpole 3 feet from its base. So let's say it's something on the flagpole, maybe that thing that they wrap the rope around, and it's right here. Well, it would also be casting a shadow from the sun, and let's just say it's here, even though the sun's not over here. But let's just say that's what it would look like. Say the sun's up higher, creating these two shadows. So the flagpole created a shadow on the ground, and you can see that object that's on the flagpole in the shadow here. That's what this is basically saying. So it says there is a mark on the flagpole 3 feet from its base. So this distance here is 3 feet. The length of the shadow is of this 3-foot portion on the flagpole is 1.7 feet. So they're saying that this piece is 1.7. Okay, so the first thing I'm going to do is label these diagrams. My image, I will say, is going to be my triangle formed by the sun. This big triangle ABC. So therefore I also have this other triangle A, and let's call this B prime, C prime. Okay. So it's a dilation. It's smaller than the original triangle, and is it similar? Okay, so it says, assume that we know that the length of the shadow is 15, the mark on the flagpole is 3, and the length of the shadow's 3-foot portion of the flagpole is 1.7 feet. The question is, can we use sunlight and shadows to determine the length of the flagpole? Okay, so we're going to assume that this line B prime C prime is parallel to BC, and since we have parallel lines, then the flagpole is a transversal. So angle A is congruent to itself because it's in both triangles. And angle AB prime C prime, this angle here, is going to be congruent to angle B because they're corresponding angles on our transversal that cuts through two parallel lines. All right, so we know they're similar. And so since now we have similarity, we can set up proportions. So if I compare my givens, I know AC prime, so I'm going to write AC prime over AC. So I'm comparing these big, or I'm going to say small over big. And this is just to keep track of what order I need to keep everything in. So the small triangle's on top in the numerator, and the big triangle's in the denominator down below. So AC prime is 1.7, and AC is 15. Okay, well actually I don't want to write that yet. I want to set up a proportion that is equivalent to each other. Okay, so since we have a similarity, we have a proportion. So a ratio equal to another ratio is a proportion. So if I'm comparing AC prime to AC, then I also want to compare AB prime to AB. Okay, now I'm going to substitute in my givens. AC prime is 1.7. AC is 15. I'm going to set that equal to AB prime, which is 3, and what we're trying to solve for is the flagpole AB, and that is X. So in order to solve a proportion, we cross multiply. So 1.7 times X, I'm just going to show all my work, 1.7x equals 15 times 3. So I'm going to simplify now. Now we're down to a basic algebraic equation. 15 times 3 is 45. And I'm going to divide by 1.7. 1.7. So x equals... Okay, so I'm going to use my calculator. We could do this without a calculator, but we're just going to save some time here. I'm going to take 45 divided by 1.7. And that is going to give me 26.47. Okay? Okay. So my answer is the flagpole is 26.47 feet. And instead of just leaving it X, I would probably go back and say, okay, now AB equals 26.47 feet. That is the flagpole. Okay, next question. Mathematical modeling exercise 1 through 3. So these are exercises. So how about you try these one at a time, pause the video, and then come back and we'll take a look and see if what you did is correct. Okay, so mathematical modeling exercise 1 through 3. You want to determine the approximate height of one of the tallest buildings in the city. So here's my building. You're told that if you place a mirror some distance from yourself so that you can see the top of the building in the mirror, then you can indirectly measure the height using the similar triangles. So here's my mirror at O. So here's my eyes right here. One eye, I'm a cyclops, looking down at this mirror, reflecting up, and I'm able to see the point S, which is the top left corner of the building, just like the diagrams, the question stated. Okay, so we're using similar triangles. So I have a triangle here formed by this person and there's the mirror and their line of sight. I have a second triangle here. I'm going to try to draw this as neat as possible. Okay, maybe right here. Okay, so here's the other triangle. These are the two triangles that we are going to assume are similar. Okay, well, we don't have to assume they are similar because this angle here, angle SOT, is 36 degrees. So it says let point O be the location of the mirror so that the person shown can see the top of the building. So there it is. Now it says explain why triangle AOB is similar to triangle STO. So ABO to STO. Okay? So if we explain that, it's because, here's what I would say. The measure of angle AOB equals 36 degrees. And 36 degrees is equal to the triangle SOT. The measure of angle SOT is also 36. So if I say the measure of angle AOB equals 36, and 36 equals the measure of angle SOT, then by the transitive property I can say the measure of angle AOB equals the measure of angle SOT. So there's one angle that we have. So we have one angle. Now I see that ABO is perpendicular. You're standing up straight, hopefully. So the measure of angle ABO equals 90 degrees, and so does STO. So the measure of angle forgot my angle symbol here. Measure of angle STO equals 90. And by the transitive property, the measure of angle ABO therefore must equal the measure of angle STO. TO. So now I have two angles, corresponding angles in the triangle, congruent. Okay, 36 is congruent to 36, 90 congruent to 90. So by the angle-angle theorem, triangle ABO is similar to triangle STO. Okay, part B says to label the diagram with the following information. The distance from eye level straight down to the ground is 5.3 feet. So what they're saying is eye level straight down is over on this side, 5.3 feet. The distance from the person to the mirror is 7.2 feet. That's right here. The distance from the person to the base of the building is 1,750 feet. Careful here. From the person all the way to the building is 1,750 feet. And we're going to label the side of the building X. Okay? Now, the reason I was saying to be careful is we know the length of OB. We know the length of BT. So I want to know what OT is. So I'm going to show this algebraically to explain what's going on here. They gave us the entire distance and a portion. To get the other portion, we need to subtract. So I would say BT, okay, the length of BT minus the length of BO equals the length of OT. Let me say that again. From here all the way over to here, minus this little piece here, is how far the mirror is from T. So BT is 1,750 feet, and BO is 7.2 feet. So if I subtract 1,750 and I subtract 7.2 from it, then I get 1,742.8 feet. That is not correct. How about 12.8? Okay, that's correct. All right. Okay, so it's 1,742.8 feet. 50 minus 7 is 43, and then 2/10 less would be 42.8. Okay, 1742.8. All right, so this piece, OT, is 1,742.8 feet. So we needed to find that first. Okay. So B was just telling us to label this. It didn't ask us to add the answer to anything. But C says, what is the distance from the mirror to the building? From the mirror to the building is what we just calculated, and it is 1,742.8 feet. Okay, part D. Do we have enough information to determine the approximate height of the building? And if we do that, and if not, explain why, or what additional information is needed. So if I look at this, I have two similar triangles because the angles, two corresponding angles are congruent. 36 equals 36, 90 equals 90. So they're similar. I know the length of the base of this triangle. I know the length of the base of this triangle. I know the height of this triangle. I need to find the height of this triangle. That is one unknown. We can solve this. So I'm going to do the work here so I don't have to keep going back and forth. But this is the answer. This is the solution to part D. So this is D. Okay. So I'm going to set up a proportion. Little triangle to big triangle. So if I say AB, then I'm going to compare it to ST. And since it's similar, it's proportional. So if AB is to ST, then BO is to PO. So then I substitute in my givens. AB is 5.3. ST is X equals BO 7.2 and TO 1742.8. There is my proportion. I am going to cross multiply. I always multiply my variables diagonal first because I like my variable on the left. It doesn't matter, but I like it to say x equals when I'm done, not a number equals x. So I get 7.2x equals, and then I'm going to multiply 1742.8 times 5.3. So I get 7.2x equals, let's grab the calculator, and I'm going to take 1742.8 times 5.3, and I get 9,236.84. Okay, to finish this, I want to know what x is. I need to divide it by 7.2. Divide both sides by 7.2, and finally the 7.2's cancel, and I get x equals. Grab my calculator and take that answer that I got in my last and hit divided by 7.2, enter, and I get 1,282.89. Okay, I'm going to go out 4 decimal places. 0.44, 0.8944. So the height of the building is 1,282.8944 feet. There should be a foot symbol there. Okay? Okay, number 2. A geologist wants to determine the distance across the widest part of a nearby lake. The geologist marked off specific points around the lake so that the line containing DE, right here, let me change color since he used black, DE, the line containing DE, would be parallel to the line containing BC. Okay, so they're telling us that these two lines right here are parallel. So I'm going to mark that. That's parallel to that. The segment BC is selected specifically because it is the widest part of the lake. That's what we're trying to calculate. The segment DE is specifically selected because it's short enough distance to easily measure. So he measured from here to here because that was easily done. So he could measure here, walk over to here, and measure there. But maybe he doesn't want to walk all the way down here. Maybe there's poison ivy or something, or it's a huge lake and it's miles and miles long. So, okay. So the geologist sketched the situation as shown below. Has he done enough work so far to use similar triangles to help measure the widest part of the lake? Okay, so keep in mind, we either need 2 angles, which is angle, angle, or we need proportionality. Some side of a big triangle over little equal to some side of another side of the big triangle over the little. So these are the 2 things we need to do: angle, angle, or proportionality. Well, I know the measure of angle A is shared in these 2 triangles. So I have this triangle here, and then I have the bigger triangle here. So obviously, as you can see, the angle A is in both. So angle A, the measure of angle A, equals the measure of angle A, obviously. Okay? All right, so I have one angle equal to another angle pair. A pair of angles equal. Since we know these lines are parallel, then I know that the measure of angle E is equal to the measure of angle C, because corresponding angles are congruent if we have parallel lines. So what they're saying is here is we have these 2 red parallel lines, and we have this transversal here. So when you have a transversal and a parallel line here and a parallel line here, then the angles that are on the same side of the left side of the parallel lines in this case, and both to the right of the transversal, are called corresponding angles, and they have the same angle measure. So he has done enough work to do similar triangles. The answer is yes. Okay? Because we know this. So the answer is yes. He has done enough work. Okay? Because we're using angle. All right, now let's clean this up a little bit, get everything out of the way, go back to the beginning. Okay. B. The geologist has made the following measurements. DE is 5 feet, AE is 7, and EC is 15. Okay, DE 5, AE 7. So DE is 5 feet. AE is here, is 7. And EC is 15. I love when problems go to the next page. So EC is this piece right here. That is 15 feet. That is just from here to here. It's not the whole AC. So this little piece is 7. This big piece is 15. So I'm going to start right now by finding AC. So if I take the length of AE plus the length of EC, then I'm going to get the length of AC. So 7 plus 15 equals 22. Actually, let me do it correctly. We're finding AC. So I should still call this side AC. And 7 plus 15 is 22. And that's what AC equals. Okay. Does she have enough information to complete the task? If so, determine the length across the widest part of the lake. If not, state what additional information is needed. So let's take a look. So we have a little triangle where we know this side. We have a big triangle that we don't know this side, and that's what we're trying to find. We have a little triangle, we know this side. We have a big triangle that we know this side. So yes, we have enough information. So I'm going to solve this here, but this is actually the solution to part B. Okay? So I'm going to write B here. So I'm going to set up a proportion. Little triangle over big triangle. And I'm just going to leave that there to remind myself not to mix things up. This side of the little triangle is AE. And the side of the big triangle is AC. And that is going to be equal to the little side here, which is DE, and the big triangle side, BC. So here is my proportion that we're going to solve. I just used this to keep everything straight. Now I'm going to substitute in my givens. AE is 7. AC is 22. The sum of those two equals DE 5. And BC is what we're trying to find, the width of the widest part of the lake. As I said before, when I cross multiply, I always choose the diagonal that has the variable, so it's on the left. 7 times x is 7x equals 22 times 5. 7x equals 110. Divide by 7, divide by 7. X equals 7 goes into 11 once with a remainder of 4. 7 times 5 is 35 with a remainder of 5. 7 goes into 50 7 times, remainder 1. 7 goes into 10 once. That's far enough. X equals 15.71 feet. Okay, so that's the answer to D. Okay, 15.71 feet is the width of the lake at the widest part. C says, assume the geologist could only measure a maximum distance of 12 feet. Could she still find the distance across the widest part of the lake? What would need to be done differently? Okay, what would need to be done differently? Yeah, that makes sense. Okay, so what they're saying is she has a tape measure. Okay, so if you have a tape measure, all right, and you pull the tape measure out, and it's got that little thing that you hook it to, and this distance is only 12 feet. That's what they're telling us in this part. Well, if you look here, if I am standing at E and I hook this hook on a tree or something here, and then I walk and whoops, right there I run out of tape. The tape ends right there. It stops. I'm short. Can I make an adjustment here so that I can measure? And the answer is yes. So if I have this segment here, so if I'm measuring from here to here is 7, and from here all the way to here is 15, 15 is too long, so I need to shorten this distance here by moving this line here somewhere along this green line. Okay, I got to move that around somewhere. So where would it have to be? At most it can only be 12. So if I moved that from here 3 feet this way, then now this length would be 12. Let me erase this piece here, get this out of the way. Okay, so I need to move this from here to here to get this down to 12 feet. Well, if I move this 12 feet, this is a distance of 3, so I'd have to add 3 this way, so this would be 10 feet. So then my triangle would be over here instead of here. It'd be this bigger triangle. And now this would be 10 is to 22 as, and this obviously would have extended in length as well. So if that is 5 here, and I drag this out here, I'd have to have extended it to this side over here, so that could be longer too. So there's the explanation, and I'll bring in the answer key solution. I explained it in the diagram, but here's the solution. Okay, so it says the geologist could still find the distance across the widest part of the lake. However, she would have to select different points, D and E, at least 3 feet closer to point B and C respectively. That would decrease the length EC to at most 12 feet, which is what I showed in the diagram. Then DE in its new position would still have to be contained within a line that was parallel to the line containing BC in order to calculate the desired distance. Okay, really hard to understand, but if you have this picture, hopefully that helped. In other words, move DE over 3 feet to the right to make this 15 segment only 12, and adds 3 to 7 and get 10. And then this would have to extend as well. Okay. Number 3. Okay, example 3. A tree is planted in the backyard of a house with hope that one day it'll be tall enough to provide shade to cool the house. A sketch of the house, tree, and sun is shown below. So here's the house, here's the sun, here's the tree. So at this time of day, they want that tree to grow up high enough to block the sun and shade the house. So they want to know how tall the tree would have to be, I'm assuming. What information is needed to determine how tall the tree must be to provide the desired shade? So we want to know that the tree has to be this tall. That's one thing we want to do. We want to know this value. What do we need to know to find that? Okay, we have 2 triangles. Let's just say here's the point where we're going to create the other triangle, the edge of this house right here. So I need to know that. So I'd need to know this length here. And so if I had this angle A and this point here B and this point here C, it says what information would I need to know? Well, I would need to know that BC, segment BC, is parallel to the tree, and let's call that DE. I would need to know that BC was parallel to the tree, DE. That's one thing. So I have 2 right triangles, so now I know that angle ACB is congruent to AED, because we're sharing an angle A here, so I'd have angle, similarity, but I would need to know BC is parallel to DE. Okay, so that would prove the 2 triangles similar, but we'd also have to know the length of AC, how far we were from this angle measurement point, the end of the shadow from the sun at this given time, to the house, So I would need to know the length of AC. Actually, that's segment AC. I would need to know the length of AC, which I could just say AC, or the length of AC is absolute value of AC. And I would have to know the length of AE. Okay, so if I knew AC and I knew AE, then I can set up a proportion, little triangle to big triangle, but then I'd have to know the height of the house as well. I would also have to know BC. Okay, so we would need to know that BC is parallel to DE to produce similar triangles, and I'll draw them here. So we have this triangle here, ACB, and we have this triangle here, AED. So if I know those two triangles are similar, I can set up a proportion of sides. Okay, so parallel. We know angle A is congruent to itself, and if they're parallel, angle ACB is congruent to angle AED. And then I'd have to know the length of the point the shade starts to the house and the point the shade starts to the tree. That would be enough information. B says, assume that sun casts a shadow 32 feet long from a point on top of the house to a point in front of the house. Okay. Okay, so if the sun casts a shadow 32 feet long from a point on top of the house to that angle there, then they're saying that AC is 32 feet. So AC equals 32 feet. So I'm going to do my work here so I don't have to keep going back and forth and writing and going back. And so the next thing says, the distance from the end of the house shadow to the base of the tree is 53 feet. So the end of the house shadow, which is A, to the tree, which is AE, equals 53 feet. And finally, I'm going the wrong way every time. It says, if the house is 16 feet tall, how tall must the tree grow? Okay, so the house is how many feet? 16. All right, so BC equals 16 feet. So this is 16, and this whole shadow here is 53 feet. Now I can set up my proportion. So I know AC and I know AE. So I'd say AC is to AE as BC is to BE. So this little triangle side here is to the big triangle side, as this little triangle side is to this vertical triangle side where the tree is going to be. I plug in my givens. AC is 32. AE is 53. BC is 16. And I don't know the height of the tree, and that's X. When I cross multiply, I do the variable first. 32 times X equals 53 times 16. Moving my work up here, I will get 32X equals 53 times 16 is 848. Divide both sides by 32, and we find the tree's required height to shade. 848 divided by 32 is 26½ feet. Okay, so that's how tall the tree has to be. Now it says, assume that the tree grows at a rate of 2.5 feet per year. If the tree is now 7 feet tall, how many years will it take the tree to reach the desired height? Oh, this is a good additional question. So 2.5 feet per year, so per year means that multiplied by year, so 2.5 times the number of years. So if it's 1 year, 2.5 feet, 2 years, 5 feet, and so forth. But the tree is now already 7 feet. So then we have to set that equal to our answer, and our answer was it had to be how many feet? 26.5 feet tall. So 2.5 feet per year, plus it's already 7 feet tall, would have to equal 26.5 feet. So there's my equation to solve. I need to know how many years, that's why. So I subtract that 7 feet off because we've already got 7 feet, so we have to subtract and see how many more feet the tree has to grow. So that's why we're adding and subtracting this 7. So 7 minus 7 is 0. 2.5 times y is still 2.5y equals 5 minus 0 is 5. 26 minus 7 is 19. So if the tree's already 7 feet tall, it needs to grow another 19.5 feet, and it grows 2.5 feet a year. Now we can find how many years it will take. So I divide both sides by 2.5. These cancel, and I get y equals 19 divided by 19.5 divided by 2.5 is 7.8. Okay? How many years will it take for the tree to reach this desired height? 7.8 years, or I could say y is equal or approximately 8 years. Okay, that was a good question. So, that is the end of Lesson 12. Go do your problem set.